Hi everyone. Um, Checking the audio levels and 6 people. Okay, let's start. Today what I'm going to do is I'm just going to solve 3 problems on conservation of momentum, and they're meant to help you with the assignment. There's actually also some other questions on the assignment on center of mass. I don't have any center of mass problems today. They're kind of easy. We'll do some next week rather than today, okay? Because I'd rather concentrate on the harder parts of conservation of momentum, okay? Let's just start then. So the first question I have here is uh, just a simple collision. So imagine that you have a linear air track, and you've got these 2 gliders, and I guess they're big gliders because one of them is 6 kilograms. Okay, so you have a 6 kilogram mass, and it's traveling to the right at 4 meters per second. Okay, now that to the right or left is important because momentum is actually a vector, and so if you're talking left or right, that's going to be the difference between a sign. And when we do these problems, I mean, I guess you should draw pictures to show which direction is positive and negative. I don't know if we really need one for something this simple. You could just say, look, right is going to be positive, and that's good enough. Okay, but in general, especially when it gets to 2D, we'll need diagrams, and you'll see that in my last question. Okay, so a 6 kilogram mass is traveling to the right at 4 meters per second. That means that 4 meters per second, we'll use it as positive. Okay, and it's going to collide with another mass, 5 kilograms, and it's traveling to the left at 5 meters per second. Okay, and left, that's going to be negative. All right, now in these problems, don't assume that energy is conserved. Okay, and the reason is that during a collision, there could be energy which gets transformed into heat. In other words, energy is lost. All right, so don't make that assumption unless I say that. All right, in fact, I could even say here, don't assume that energy is conserved. In fact, that's going to be one of the questions. All right. So how do you do this? Well, oh, sorry, I got to tell you the after. That's the before picture. The after picture. Uh, the after picture is actually there's going to be collisions and pieces, and pieces are going to be sticking together, coming apart and sticking together. And I actually said here, a collision happens, and when these pieces break apart and stick together, then the masses are going to get reconfigured. But don't get caught up in the detail. And I have some questions like that on the assignment too. Don't worry about, I even tell you, not as a red herring, but it's an ignorable fact. I say, well, a 1 kilogram breaks off from this one and attaches to that one. You don't have to worry about any of those details, because this is the whole point of a conservation law. In a conservation law, the intermediate details are unimportant. Even things like, do the masses break apart and reconfigure themselves? Okay, and so I say here, don't get stuck in the details. So collision happens, things break into pieces, and they stick together, and you wind up with 4 pieces afterwards. And here's the description of that. Okay, let's see here. Okay, here's the description of that. So we have a 2 kilogram mass moving to the left at 10 meters per second, a 3 kilogram mass moving to the right at 3 meters per second, and a 4 kilogram mass moving to the left at 2 meters per second. Now that's only 3 pieces, and now we're ready for the questions. Okay, question is, how big is the remaining piece? Okay, well, that's kind of obvious. Normally I don't even ask this question, but since we're talking about conservation laws, conservation of matter, conservation of mass is actually a conservation law, because if you mix things up or break things apart and recombine them and so on, the total mass has to remain the same. Okay, and so oh, I think I did my solution wrong. That's okay, we'll fix it in a second. So we have 6 kilograms and 5 kilograms, and together, what's that equal to? That's equal to 11 kilograms, right? Okay, so if we have 11 kilograms, that means here, how big is the remaining piece? We could say here that the total mass is 6 plus 5 kilograms, which is equal to 11 kilograms. Okay, and now what do we have here? We have a 2 kilogram mass, right? We have a 3 kilogram mass. We have another 3 kilogram mass. Oh, sorry, no, a 4 kilogram mass like that. Okay, and then we have an unknown mass, and I guess we could just call it M. Actually, let's call it M4 like that. You spread these apart. Okay, so there are 4 pieces. And what's this got to equal? Well, 11 kilograms. Okay, and that means that M4 is equal to what? What's that? Did I do this right? 2, 3, and 4. Yeah, okay, so that's 4, 7, 8, 9. So that's 11 minus 9, which is equal to 2 kilograms. So the remaining piece must be 2 kilograms. Okay, so great. There we go. And there's a very simple example of a conservation law, in this case, conservation of mass. All right. So notice how I did that problem. Okay, I went kind of fast because these are kind of easy, but notice how I did that problem. I said, look, what's the mass before? So you could even say here, this is the before. Okay, so what's the mass before? It's 11 kilogram. Well, what's the mass after have to be? The mass after has to be also 11 kilograms. And you say, well, I don't know all the pieces. That's right. Because the total has to add up to 11, that M4 must be 2, okay? And so that's the same way we're going to do the momentum problems, conservation of momentum. Okay, so next question. How fast is that piece moving? Okay, that is that last 2 kilogram piece. All right, so uh, we proceed the same way. We calculate the total momentum before, and there it is. Okay, so how is momentum calculated? So total momentum is going to be, well, momentum of any one piece, no matter how many pieces there are, is m times v, the mass times the velocity. Okay, and if you've got 2 pieces, it's going to be m1 times v1 plus m2 times v2. If you have 4 pieces, then you do the same thing for piece 3, piece 4, and so on. So you just add mv, 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 mv for all of the pieces, and that gives you the total momentum. Well, before this complicated collision, we only have 2 pieces, and so P is going to equal m1 v1 plus m2 v2. Okay, and when we substitute in the numbers, we have that the 6 kilogram piece was moving to the right. In fact, let me put a little plus in there like that. Okay, so it was moving to the right at what was it, four, is that right? Yeah, 4 meters per second. Okay, and the 5 kilogram was moving to the left at 5 meters per second, and so 24 plus negative 25, that's -1. Okay, and there it is. And now the units here, I gave them in MKS units, so that's 6 kilogram in meters per second, and that's also kilograms in meters per second. There isn't really a name for the momentum unit like there is joule for the energy unit, but the MKS unit would be kilogram meter per second. Okay, so there you go. That's the total momentum. That doesn't change. It's the same before. It's the same even during that complicated interaction when I haven't given you the details. No matter what's going on, I mean, there might be intermediate steps where pieces are breaking off and recombining and so on. Even at every stage, no matter how complicated it is, that's the total momentum. And then after, I said there are 4 pieces. Okay, and so now the equation for momentum after is going to be this. Okay, that one right there. Okay, now it looks the same, but it's for 4 pieces, and the little primes there. That's just how I did after. Like earlier in the course, we had like little subscripts, but there's so many subscripts in this business that I just thought instead of trying to do another subscript, just do a superscript. So at least for the momentum section of the course, the little primes mean after the collision. Okay, and so after the collision, there are 4 pieces, and so there's going to be 4 contributions to the total momentum. There's one, there's another, there's another, and there's another. Okay, and so now we just substitute in, and we know that the pieces are a 2 kilogram traveling to the left at 10, a 3 kilogram traveling to the right at 3, a 4 kilogram traveling to the left at 2. Okay, and so let's put that in there, and then finally we have m4. That has to be the 2 kilogram multiplied by that velocity there. Okay, and here's that. Okay, except that I made a mistake when I did this, so let me just change that to a 2. There we go. Okay, so there's the substitution. All right, now what did I do there? Well, the momentum after, that's -1. Why? Didn't change, right? So whatever you calculated for the momentum before, that's also equal to the momentum after. All right, so that's where that -1 is. And we had a 2 kilogram traveling to the left. Okay, let me just check that. 2 kilograms traveling to the left. Right. Left is negative. Okay, we had a 3 kilogram traveling to the right. Okay, I put the plus in there just to indicate that it's to the right. A 4 kilogram traveling to the left. Okay, and then finally we have a 2 kilogram traveling at some unknown velocity. Okay, that's what we want to find because that's the question. How fast is this piece moving? Okay, and so now it's just a matter of some simple algebra, which I got wrong, but I mean I'll be able to fix that pretty quickly. All right. So if you're copying this down, just give me a second to fix this tiny error that I made there. That should be a 2 there, like that. Okay, so if you here's a -1. If you calculate all of this, it turns out to be -19 and then 2, and that means that you're going to get 2 times V4 is going to be equal to this, and that means that V4 primed, oops, is going to equal 18 divided by 2, positive 9 meters per second. Okay, so the last 2 kilogram piece is moving to the right. How do we know that it's to the right? Positive, like that. Okay, and it's moving to the right at 9 meters per second. All right, so that's that should have been pretty straightforward. Let me see if you've got any questions in the chat. Okay, good. All right, let's continue. So the first one is, like yeah, I give you the details before, I give you the details after, but I'm missing one detail. What am I missing? How fast is one of the pieces moving? And because momentum is conserved, because those two are equal to one another, you can calculate that last value. And there it is. Okay, that value has to be such that the momentum is conserved. All right, so the next question is, what's the energy before? Okay, so during these collisions, like I said, there can be friction. Okay, and if there's friction and energy gets lost as heat, then that's an inelastic collision. Okay, if there's energy created, and you say, well, how can energy be created? Well, it's not really created. It comes from chemical bonds, and it goes into the motion of the particles of the pieces, and that could be that can mean there could be extra energy afterwards. Like, just think, during the collision, something explodes, and then the things fly apart faster afterwards. You would see that if you just looked at the motion of the things, that you would have more energy after, and so that's a superelastic collision. And if the energy before and after are the same, that's called an elastic collision. Okay, and so what's the energy before? Well, there's only two things moving, and the energy is calculated as just 1/2 mv squared. So there's no potential energy in these problems. Okay, so now there's the kinetic energy for the first mass, okay, and there's the kinetic energy for the second mass, and there's no potential energy because there's just none involved in these problems. Okay, they're just moving along, and they're not interacting, and then they come together and they collide, and then they interact. Okay, and so so you just have the kinetic energy of the first one plus the kinetic energy of the second one, and that gives you the total energy before. Okay, and just substituting in here. Okay, we have for M1, that's the first mass is 6 kilograms, and it's traveling at 4 meters per second. Okay, the second one was 5 kilograms, and it was traveling at 5 meters per second. And you'll notice that I dropped the negative sign, like I had it up here for the velocity, but I dropped it there. And you go, well, why did you drop the sign? When it comes to energy, the sign doesn't matter, because when you calculate the kinetic energy, the velocity comes in squared, and whenever you take a negative number and you square it, you get a positive number. So the fact that this is actually -5 squared, -5 squared is the same as 5 squared, it's 25. Okay, and so I didn't put the negative sign in there. Okay, so when you work that out, you get 110.5 joules of energy. That's the energy before. Okay, so now what about the energy after? Okay, well, the energy after the collision, same idea, just add up 1/2 mv squared for each of the moving pieces, but now there are 4 moving pieces. Okay, and so your equation is going to look like this. All right, so it's structurally the same equation, but it's got extra terms because they're just more pieces, but each term has the exact same form. So if you take a look here, this is 1/2. Oh, I guess I should probably put primes on this, because these are the masses after the collision, like that. Okay, so we have 1/2 m1 primed v1 primed squared. Okay, and that could be like the very first piece, the first fragment after the collision. That would be this 2 kilogram mass right here. Okay, the 2 kilogram mass moving at 10 meters per second to the left. Okay, now left is negative, but again, when we substitute, we could just drop that negative sign because it'll be v1 prime squared, and negative 10 squared, it's the same thing. It's equal to 100. Okay, so so structurally each term is the same, 1/2 mv squared, but there's four of them. There's the first piece, there's the second piece, there's the third piece, and there's the fourth piece. Okay, so substituting in, we have this, but give me 1 second because that should have been a 2, and that should be a 9. Okay, so let's see what I did there. So 1/2, I just wrote that as 0.5. Okay, and the first piece was 2 kilograms traveling at 10 meters per second. First piece after the collision. So all of this is after the collision. Okay, so that's why I call this one M1 primed and that one M1, because the pieces before and the pieces after, we don't even have to worry how they rearrange. They did rearrange. Okay, and so one of the pieces, what we're calling the first piece after, that's 2 kilograms traveling at -10, and again I dropped the negative sign. Okay, the second piece was 3 kilograms traveling at 3 meters per second. The fourth piece was 4 kilograms traveling at 2 meters per second. And the third piece, and then the fourth piece was that remaining 2 kilograms traveling at 9 meters per second. And so where did you get that? That's what we calculated up here. Okay, so we found that the last piece had to be 2 kilograms in size, and it was traveling at 9 kilograms per second. Okay, so give me just 1 second to calculate this because the number I have is obviously wrong. And it turns out to be E primed is equal to 202.5 joules. Okay, so 202.5 joules. All right. So everyone good so far? Let me check the chat here. Also give you some time if people are writing this down. Okay, great. And so the last question is this collision elastic, inelastic, or superelastic? So for that, just compare the energies before and after. So the energy before is 110.5, and the energy after the collision is 202.5. The energy after is bigger than the energy before. Again, you say, well, how's that possible? Energy is supposed to be conserved. Yeah, we didn't really trace it all down, but say at the microscopic levels, there was a little bit of some like nitroglycerin or some, not much, because this is not a lot of 100 joules is not much energy, but maybe just a little tiny explosion as the things were breaking apart and recombining, and so the energy after is a bit more than before. And you could actually have a combination. You could have energy being released in one place and being turned into heat in another place, but just the energy that's being released into heat from the explosion is more than the energy of the that's dissipated as heat. And so you could you simply have that there's more energy after than before. Whenever the energy is greater after, that is called super elastic. Okay, and there it is. All right, now if the two had been equal, so that's the answer, but just to since we're reviewing, just to say, if these two had turned out to be equal like that, that would be called elastic. And if it turns out that the energy before is less than the energy after, which is like 99% of all collisions, energy is turned into heat, then then you have an inelastic collision. Okay, but in this case, just to be a little different, I decided to create an elastic collision where there was more energy afterwards. Okay, so is everyone good with that? Let me take a look here in the chat. And hopefully I'm not going too fast. If you're taking notes, I don't want to go too fast. Don't be afraid to just say, hey, slow down a bit, okay? All right, well, there's our first question, okay? And let's do our second question, okay? So the second question is a pretty hard question. I even said that down here, okay? And I'm going to show you a technique on a test for being able to do this question quickly, okay? But right now, let's do it how should I put it, the long way or the proper way to do it, okay? And you'll see that there's a lot of algebra in it. Even though it looks like a pretty innocent problem, there's a lot of algebra in it. And like I said, on a test, I can show you how to speed that up, okay? So what does it say? Well, we have the same situation as before. We have a 6 kilogram mass, and it's traveling to the right at 4 meters per second, okay? And it's going to collide with that 5 kilogram mass traveling to the left at 5 meters per second. So far, it's the same as before. But this time, I tell you that the collision is elastic, okay? And I ask, how fast are the two masses afterwards, after the collision, okay? And you go, well, why is this hard? And the reason that it's hard is because both, I better write this down, both momentum and energy are conserved. Now, the reason that gets hard is the conservation of momentum. We just did a problem like that. That's easy because, you know, the velocity comes in linear. In other words, it's not squared. But with the energy comes in squared. And what you have to do is you actually have to take one equation and put it inside another, and there's no way to avoid a quadratic. Well, that's not totally true. It depends on the problem. The problem I did during the pre-recorded lectures, I purposely did an easy problem, maybe too easy, okay, which is why I'm doing it now. And there I had it so that when you solve the quadratic, it was trivial. But in general, you know, it's solving a quadratic, and there's no way around that, okay? So let's see how we do this problem. Okay, so let's start off with momentum. So you analyze momentum and energy separately, okay, and then bring the two together. Let's start off with analyzing the momentum. So the momentum is, it's basically a repeat of above. We have this for the momentum before, right here, okay? So maybe I should even say here, before, okay? So here's the before situation. The before situation, there are only two pieces. By the way, there's only two pieces in this. Okay, so nothing's breaking apart, nothing's recombining. Okay, I didn't say that, but it's kind of implicit, you know, in how I asked the question: how fast are the two masses moving afterwards? Nothing's breaking apart, nothing's recombining. The two masses just come, they hit one another, and they fly apart, and it's elastic. There's no energy gained or lost during this. Okay, so let's start off with momentum. So momentum, say here, P before, okay, momentum, capital P before, okay, momentum before. So the momentum before is just m1 v1 plus m2 v2, like above. And when we calculate that, you know, nothing's changed here, so it's again -1, and the units are kilogram meters per second. All right. And what about the momentum after? Okay, so the momentum after, P after, looks like this. It looks like the same formula, obviously, only what's different? Well, the masses stay the same. So M1, say our 6 kilogram mass, that stays the same. And M2, our 5 kilogram mass, that stays the same because that, like I said, they didn't break apart or anything. Okay, but the velocities change. So instead of V1, we're going to call it V1 primed, okay? Now, that little prime there, that's important because those are actually different numbers. Okay, so even though the symbols look the same, doesn't mean the numbers are the same at all, okay, or even close. So again, V1 just means the velocity of number 1 before, and V1 prime means the velocity of number 1 after. And of course, you know, before, you know, the velocity of the 6 kilogram is positive. After, it's probably going to be negative. In fact, I know it's going to be negative because I solved it, okay? So so there it is. And V2 prime, same thing, okay? Now, when we substitute in here, you're going to go, okay, so I know that M1 is 6, and I know that M2 is 5, okay? And we sort of chose, you know, to name them that way. Okay, that's implicit right here. See, M1, I just said, okay, M1 is 6 and M2 is 5 there, like that. So M1 is 6 here and M1 is 5. But we don't know V1 primed and we don't know V2 primed, okay? Now, there is that P primed, and you say, well, what's that P primed equal to? Conservation of momentum. It's actually equal to -1, like this. And you look at this and you go, now what? Now what? Well, because you've got two unknowns, and that's the point. You can't solve this by itself. I didn't give you enough information, enough direct information. I didn't tell you V1 primed. I didn't tell you V2 primed, okay? So you can't solve this one by itself. What you got to do is you're going to have to take this one and insert it into the conservation of energy, which we'll look at next, okay? And then you'll be able to solve it. Of course, in doing that, that quadratic comes out, okay? So I hope everyone's with me so far, all right? So just rearranging this so that it looks a little bit neater. It's going to look like this. Oh, that's just a repeat I over. Okay. So there's this, and then what I did, I did this in too many steps. So here I have -1 on this side, and what I'm going to do is I'm going to subtract -6, oops, like this from both sides, and that will isolate the 5v2 prime like that. Okay, so uh, over here I just subtract 6 v1 prime from both sides, so I get -1 minus 6 v1 prime there, and that's going to equal 5 v2 prime like that. And then I don't know why. Well, I don't know. I do know why, but I just kind of like switch the two sides around. Hopefully, I'm not being too pedantic here. I just switch the two sides around like this, and then divide it through by 5, and I get my equation number 1. Okay, so that's what I did there. Okay, now the idea is to isolate either v1 primed or v2 primed. I decided to isolate v2 primed. Okay, you'll see why in a minute. Okay, you'll see why in a minute. All right, now that's really hard to read, so you don't have to worry about why I did it here, but when I go to solve it later, you're going to see that there's so many symbols around, it's just easier to call v1 primed x and v2 primed y. Okay, nothing magic there. It's just because when you see the equations later, they're gonna drive you crazy with all the symbols. So that's all I'm doing here. Instead of writing v2 primed and v1 primed, I'm just going to write y and x there like that. Okay, so don't let that be mysterious for you at all. It's just, in other words, you can even just ignore this for now, okay? It'll just become easier when we get to it later, all right? So you can't get any further because you don't know x, you don't know y, you can't solve for this problem. Okay, so now what? Well, let's now do energy before. We actually did this, above because nothing changed, but, redoing the problem, so let me go ahead and just cut and paste all of that information there, like that, okay? And so what do we have here? So what we have here is we have the total energy is the sum of the two kinetic energies. And just like above, it's 1/2 m1 v1 squared plus 1/2 m2 v2 squared. This is before the interaction. And then substituting in all the numbers, you get that 110.5, just like we did above. Okay, so nothing new there. Okay, what about the energy after? Well, the energy after is going to be this. Actually, let me just cut and paste all of this so I don't have to keep going back and forth. We'll just go through it one step at a time. It has the exact same, the equation has the exact same structural form. There it is, like that, okay? So it's again 1/2 m1 v1 squared and 1/2 m2 v2 squared. But instead of v1, it's v1 primed, the velocity after the collision. And instead of v2, it's v2 primed. So there and there like that, okay? And I did the same thing again. I double cut and paste here. Okay, now substituting in the numbers, we can reduce this. The energy, well, what did I say? The energy is the same as before because this is an elastic collision. So that's that little line there, right here. That little statement right there. The collision is elastic. That's crucial to solving this problem because it allows you to equate E1 to E1 primed. Okay, so over here, for E primed, in general, if you say, I don't know if this is elastic or inelastic or what, you can't say that E primed is equal to E because it might have gained energy, it might have lost energy. In this case, we can say that E primed is equal to E because it's elastic. In fact, I could even write that in here, okay? So maybe I'll just say, note E primed is equal to E because this is an elastic collision. All right? So there it is. Now substituting in all the numbers as far as we can, you get this, and you have v1 primed and v2 primed. They're like that. Those are unknown. Okay, and so just to make life a little bit easier, I don't like that 2.5 there and that 10.5. That's not a big deal. You can certainly work with them, but I just decided to multiply by 2 on both sides to get rid of the 0.5s. Okay, so Uh, um, Again, don't let that be mysterious at all. I'm just trying to make this as easy to see as possible. If you work this through and you didn't multiply by 2 on both sides, it work out just fine, okay? So if you multiply 110.5 by 2, you get 221. If you multiply 3 by 2, you get 6, and if you multiply 2.5 by 2, you get 5, okay? I actually did that in the pre-recorded lectures. I thought I'd repeat it here just because someone asked me, how did you get from one to the other? That's what I did, okay? And I probably should have said, that I did this to get rid of the halves. Okay, you see these halves right here? They're kind of annoying sometimes. I mean, not if the numbers are even and they divide out, but they're not. So I get this 2.5, and I just thought, I'd multiply by 2. It's not a big deal, okay? And then the other thing I did is, because now this is going to start looking like that equation is really hard to read, I think, okay? And so nothing magical. I'm just going to call v1 primed. I'm just going to call it x, and just for v2 primed, I'm going to call it y, okay? Not to be confused with x and y coordinates or anything like that. I just needed, you know, some simple variables that are easy to see, and I called that one equation number 2. Okay, so at this point you're going, geez, this is a lot of work. Yeah, it is. Okay, hang on, I've got a trick. I told you, I promised you a trick. So there's equation number 1, and there's equation number 2. And we had this sort of a situation when we did Newton's laws, and we had the two masses. You got two equations, two unknowns. But there it was easy to solve, the two equations and two unknowns. And now it's not so easy to solve. And you go, geez, how do I do this? Let's take a look at what the problem is. I'll put the two equations, side by side. Okay, so here's equation number 1. I'll put it here. And here's equation number 2. I'll put it below it. And you go, geez, how do I solve these two? It's not a matter of just adding the two together like we did before. That's not going to work. What you have to do, unfortunately, as ugly as it is you're going to have to take that y there, which is this entire expression, and replace that y in there. Okay, there's no other way around that. All right, so to solve, let's say that over here. To solve, substitute equation number 1 into number 2, eliminating y. Okay, so here's equation number 1, just to remind you, and here's equation number 2, just to remind you what that one looked like. And so what I'm saying, what this would mean, substitute 1 into 2. So here's equation number 1, and substitute that into number 2, eliminating y. What that means is you take equation number 2 there, but instead of y, I'm going to put square brackets here. Okay, you say, well, what goes into those square brackets? All of y. Well, where's y? There it is right there. I mean, it was y, like that, but equation number 1 says that y is equal to this whole mess, like that, and so there you go. Okay, so that's what this English means. It means you take number 1, you substitute in number 2, and you eliminate y. Okay, so there we go. Let me see if there's any questions in the chat so far. Oh, people seem to be doing pretty good. All right, so now what? Well, the rest is solving for x. But you could see exactly what's going to happen. X is going to be a quadratic, okay? And so let me just cut and paste that. I will go through it slowly, but there's a lot of steps in here, so I'm just going to cut and paste them all. Yeah, I'm going to cut and paste all of this. As I promised, there is a quick way to do this on a test, which you'll see why. Okay, so that was a lot of steps in there. Okay, so where had we gotten to? We were up to this point here. Okay, now the rest really is algebra, but I'll walk you through it. See the negative sign there and the negative sign there? Well, we're squaring it, right? And when you square something, you can just change the sign. So negative, if I multiply throughout in there by -1, it becomes positive like this. Okay, now I hope that wasn't too mysterious for you, but again, like here, just off to the side, I'll erase this in a second. Well, you can't see that. Now you can. If you have like like -1 minus 3, and you want to square all that, okay, like that. All right, you say, well, what's that equal to? Well, I mean, you could do it this way. You could say, okay, that's going to equal -4 squared. And what's -4 squared equal? -4 times -4 is 16. Okay, that works. Here's what I did. I didn't like the negatives. Okay, let's get rid of this piece right here. I didn't like those negatives. So I said, you know what? I'm going to take this whole thing and multiply through by negative. So that's going to become positive, and then that's going to become positive. And so then I get it 1 plus 3. And that's going to equal 4 squared. And what's 4 squared? 16. It's the same answer. Okay, so all I did here is because I didn't like that negative and I didn't like that negative, I multiplied the whole thing by negative and it just turned it all positive. Okay, so again, it's just to make the algebra as easy to read as possible, easy to go through as possible. Okay, so now we're here. Now what? Well, we got a polynomial, right? Polynomial, we've got a binomial there. So remember how you work these out. It's this squared, all right? So that's 0.04. And then it's going to be that multiplied by that, multiplied by 2. So 0.2 times 1.2 times 2. And that gives us 0.48, okay? And that's the x term, the linear term, okay? And then plus that squared, and that's 1.1 squared is 1.44. Okay, so that's what happened to get there. Okay, and then what did I do? Well, it's 5 times all of that, so I multiplied through by 5. Okay, so I did 5.04, and then 5 times that, and 5 times that. Okay, got down to this. And now what? Well, now, collect the terms. So you've got 6x squared plus 7.2x squared. And so my linear term is 0.2. Sorry, my constant term is 0.2. The linear term is 2.4 times x. And then that 6 plus 7.2 is 13.2x squared. Okay, so there's that. Okay, almost. We've got that 221 on the left-hand side. So subtract 221 from both sides. And I get that polynomial right there. Okay, oh, sorry, polynomial. It is a polynomial, but it's a special polynomial. It's a quadratic. Okay, so there we go. And then you say, well, I got to solve this using the quadratic equation. And you go, okay, what's my a coefficient? That's the coefficient in front of x squared. And what's the b coefficient? That's the coefficient in front of the x. And what's the c coefficient? That's the constant. That's 0.2. Oh, sorry, no, right here. That's the negative 220.8. And so there we go. Now we're ready to solve using those coefficients. And you could use that quadratic formula, which you've learned in high school. We did use earlier in the course when we did 2D kinematics, or even in 1D kinematics. Okay, when things going up and down, constant acceleration. But I think I gave you this site before. Okay, it's a nice little site. You could just Google for solve quadratic equation online. Okay, and like gazillions of sites come up. This is the one I like. It's called math.com. They've got a lot of simple little formula solvers like this one. Okay, so it's basically math.com student calculator source quadratic, but I don't even remember it. Like I said, I just Google for it, and I just put in these numbers. I just put in A and B and C in there, and then press the button, and then magic happens. Of course, it's a quadratic, so 2 solutions come up. And what are those two solutions? We get this one, x is equal to 4, and we get this other one, x is equal to negative 4.18181818. Okay, so I kept too many digits there, but that's okay. Now, that x is equal to 4, you say, well, what is that? Well, don't forget, the whole reason I did x was because imagine doing all this. It's hard enough to read already, doing all that, and instead of having x, I had v1 primed in all the places that I had x, so that would have driven you crazy. That's why I chose the x and y. I thought it might be just pedagogically easier to follow. But x was v1 primed. What does v1 prime mean? It means the velocity of m1 after the collision. Okay? But you say to yourself, 4, I could even say here plus 4, you go, wait a sec, isn't that the velocity before the collision? If you go back to the problem here and reread it, the 6 kilogram mass, what's it doing? The 6 kilogram mass is traveling to the right at 4 meters per second. And so plus 4, that is the original velocity. And so we didn't get v1 primed here. What did we get as one of the solutions? We got v1 as the solution. We got the velocity before as one of the solutions. And that happens. When you do these problems this way, what will happen is you'll get you'll get 2 solutions. One of them will be the original velocities before the collision, and the other one will be the velocity after the collision. So we don't want this one. In other words, we have 2 solutions, but we don't want that solution. We want this solution. Okay, we want the solution that x is equal to negative 4 point, well, rounding off negative 4.18. Okay, and that's the answer you want. That's the velocity of the 6 kilogram mass, that's m1, after the collision. Okay, and notice that it's negative, and that makes sense because you know what's going to happen. You know, if this is the 6 kilogram right here, it comes in and it's coming into the right, and then it bounces and goes out to the left. It comes into the right, but it bounces going out to the left. Comes in positive and it goes out negative. Okay, so that's working out. Okay, and now we have v1 primed. Okay, so actually I could even say that right here. That's equal to v1 prime. That is what v1 primed is. Okay, and now you say, well, how do I get v2 primed? Because there are two masses here and we want both of them. And you just go back to equation number 1 and you want to now get y. Okay, and so you know, there was equation number 1. I just repeated it there. We know x, it's a big long solution there, and so we get that y is equal to that, which I can round off to, and I'll put a little positive in there because that's actually, and actually even better yet, say that's equal to v2 primed. There you go. That is your v2 primed, and that makes sense because m2, the 5 kilogram mass, it was coming into the left and it goes out to the right. Okay, so there you go, and so I summarize that here. Okay, after the collision, the 6 kilogram is going at 4.18 to the left, and the 5 kilogram is going 4.28 to the right. Okay, there you go, and that answers the question. At this point, you're going to say, oh my goodness, if you gave me that on a test, I'd freak out. Well, okay, so I promise that there's a fast way to do these problems on a test. So how would you do this on a test? Well, on my test, just not in general, okay? How would you do this on a test? So on a test, I give you answers or possible answers, okay? And all of them are wrong but one. And so what do? You go backwards. You work backwards. And by the way, I have one like this on the assignment too. So on the assignment, there's actually two questions. Look at them both together. Okay, I forget their numbers, but they're both. You know, one is what do you get for the velocity after for one mass, and the other one's for the other one. But you know, they're two questions for the same problem. Okay, and you say, well, okay, you've given me these velocities. Do they work? In other words, work backwards. I've given you the velocities. See if the velocities conserve momentum and if they conserve energy. If they don't conserve either momentum or energy, they're the wrong answer. Okay? They're the wrong answer. And so, you know, you can save yourself of having to find the answers because you're only searching for the answers among five possible numbers. Okay? So, what do? Well, you know, like suppose I say, you know, as one of your possible answers, I say this is one possibility. I say that's A, you know, possibility number A. You go, all right, well, does it work? Well, does it conserve momentum? Okay, and so you try this and you go, well, if it conserves momentum, it better give me the same value after as I got before. But I give you enough information to calculate the total momentum before. That was that -1, down here was that -1 kilogram meters per second. Okay, that was the total momentum before. And now you've got these velocities after. Do they work? Do they still have conserve that momentum? And so, you know, you start from this equation here, which is the momentum after. You substitute in the, you know, the velocities that you think might work. Okay, in this case, you know, before it used to be +4, but now we have that. Before the collision it was +4. After the collision we found that it was -4.18. Okay, +5 before the collision it was -5. After the collision it's 0.482. Okay, and you say, okay, what does that give me for the momentum? And it actually turns out, because of round off error, to be -0.98. That's close enough to -1. Okay, so I made some round off errors above, and so that's what's going on there. Okay, sorry, that was my phone going off. All right, so momentum is conserved. Now, if I had other possible velocities there, and you did this, you know, your momentum would be totally off. Chances are I'm going to give you one where either the momentum is conserved but the energy isn't, or the energy is conserved and the momentum. Both have to be conserved. Okay, so I'm not trying to be tricky, but I'm trying to make sure that you understand that, you know, both have to be conserved. So just because you find that the momentum is conserved, don't stop, because the energy might not. Remember, this is an elastic collision, so both are conserved. And so you say, okay, great, that's the first check. That is necessary but not sufficient. I better do the other check. What's the other check? Is the energy conserved? And we know what that energy has to equal. That energy has to equal the energy before, which was the 110.5. Okay, and so you go, okay, well, let's put in the numbers here, and you can see here that I'm putting in the new velocities. Okay, and it turns out that that energy is 110.4982. And so again, within round off error, that's 110.5 joules as expected. Okay, so ask yourself, did it conserve momentum and did it conserve energy? And the answer is yes. There you go. You've found the right answer. Again, there's going to be 5 of them. It might be a little bit annoying to have to go through them until you find the right one. But you know what? If you use a little bit of intuition and you see that some of them are just like way out of the ballpark, it's just like there's no way the velocity is going to be that. So just go through them systematically, and you'll be able to answer the question. So I guess the reason I'm doing this, I want to give you problems like this, is because I want to make sure that you understand that there are problems where the collisions are both they're conserving everything. In other words, there's no friction, there's no dissipation into heat, there's no explosion, explosives that add energy to the system. And so this way I can have you do that without having to go through all the insanity. I don't know if it's that bad, but I mean, like on a test, on an assignment, I mean, I don't care, like, because you can always ask questions. But on a test, you say, geez, do you really want to have students go through all this tedium? And maybe not. Now you can. Maybe some of you will say, well, this is pretty easy, and you can go through this, and you'll get the answers, and that's perfectly legitimate. If my tests were not multiple choice, you wouldn't have any choice, because you wouldn't have any clue as to what the answers are. Okay, so I hope I've given you some indication of how to solve these problems quickly on a multiple choice test. Basically, I've given you the answers, or potential answers. Does a potential answer actually conserve both energy and momentum? It's sufficient for one or the other to not be conserved for it to be the wrong answer. Okay, so let me see if there's any questions on the chat here. Not really. Okay, good. Let's continue. Okay, so this one says see the diagram. Okay, so 2 masses collide and stick. Okay, and this is a 2D problem. Okay, so maybe I should just say here see the 2D diagram. Okay, because it's going to be 2D. So we've got one of these situations where I have a couple of masses that are coming together in 2D. They stick and they collide and they stick. Okay, and I want you to find the x and y component of the final velocity. I guess I should say here of the combined mass. Right? Because you might say, well, which mass? Well, it doesn't matter, because they're both stuck together. Okay, and find the magnitude and direction of the final velocity. So the first question, x and y, that's Cartesian. The second question is polar. Now, when you do these problems, you have to do them in Cartesian, because the way it works is that the total momentum in the x direction will be conserved, and independently of that, the total momentum in the y direction will be conserved. Okay, so let's take a look at the diagram here. All right, so there we go. So what do we have? We have, let me use a different color here, green, I guess, or red. So we have this 7 kilogram there, okay, and it's traveling at 4 meters per second. All right, and it collides with a 5 kilogram traveling at 5 meters per second. All right, and they collide. I guess they collide right here at the origin. And when they collide, they're going to stick and go off in some direction. All right, and the angle in here, that angle in there, is 60 degrees. All right, now that's the tricky one. How do you deal with the angle here? All right, and before I switch to my next diagram, maybe you should just guess, where do you think the resultant vector is going to be? And I think it's pretty obvious. It wouldn't go off that way. Okay, that makes no sense. Okay, and it wouldn't go off that way. That makes no sense. I think most people would go, oh, it's probably going to go off like that. Okay, that's your intuition. And your intuitions are human intuition with respect to momentum is pretty good. May even be genetic, like we throw things, so you got to have a good sense of, like, what direction things go when they hit things. Okay, anyhow, so you can see that this vector here has a bit of a negative y component, and this one has no negative y component, so that one has to have negative y component. And both of these vectors have positive x components, so this one has to have a positive x component. That means that way rather than heading that way. Okay, and so that's why you expect your vector to be down in this fourth quadrant here. Okay, all right, good. So now the trick to doing this is you got to split the you got to split this velocity into x and y component, and you got to split that velocity into x and y component. Okay. Well, the velocity of the 5 meters per second, that is this one right here, that one's easy to split into x and y. How come? Well, because it's going straight along the x-axis, and in fact, it's heading directly towards the positive x-axis. Okay, and so it has no y component. Okay, and you've got, I mean, there's nothing to break up. There's no you don't have to do this cosine and sine of that. You've got what it's you've got its resolution into x and y already. Okay, it's this one that's the problem right there. And what's worse is you go, well, do I use that 60 degrees there? Well, yes and no. Okay, the way you do these problems is you got to pretend, because you got to break up this vector into x and y components, and you don't want to use this angle there like that. You say, well, do I measure it from the positive x-axis? No. And the reason is that you would, if here, let me just draw a very quick little diagram here. If you had a vector like this where the head is up here, see where the head is there? Okay, then you would measure the angle like that. But look at where the head is on this vector. It's down here. The vector itself, I've drawn it in the second quadrant, but where is it heading? It's heading into the fourth quadrant. Okay, and so how do you work out that angle there? Well, that's what my next diagram is all about. Okay, so make sure you understand that this one right here, that's a problem. This one isn't a problem, but I could have given you a problem where I had like one going this way. That's what I do on the assignment, in which case you're going to have to analyze two vectors that are not, that have both an x and a y component associated with them. All right, so let's concentrate. My next slide is just going to concentrate on that vector right there. Okay, and is it going to switch on me? There it goes. Okay, good. Did that work? It did. Good. All right, so let's take a look at that diagram. This is just so this is not the collision. This is just the 7 kilogram traveling at 4 meters per second. Okay, and here's that 60 degrees. Okay, maybe I drew too much in this diagram. Yeah, I probably drew too much, but that's okay. So this is the 60 degrees. And you say, well, what angle do I use to break it up? Because you got to do 4 cosine some angle here and 4 sine some angle. You go, well, what angle do I use there? A lot of students will just blindly use the 60 degrees, and that's not right. Okay, so here's what's going on there. In order to break up a vector, the tail of the vector really has to be at the origin. And you say, but the tail of the vector isn't at the origin. That's okay. Put the origin at the tail of the vector. All right, and so actually this diagram should probably have, like, I don't like the way I drew it. This up here, that's positive y up here. Okay, see, I have an arrow there. That's not positive y there. I don't know why I put an arrow there, but just whoops, why did I do that? Undo. There we go. Put the origin at the tail of the vector there like that. Okay, so that's the first step. The next thing is figure out what this angle is. So unfortunately, I drew that angle in there already, and I probably shouldn't have done that, because the whole point of this is to show you dynamically how I work it out. But you have to work out that angle. And you see, this is an x-axis here, and here's an x-axis down here. And the two x-axes are parallel to one another, and that vector is cutting across two parallel lines. And there's a theorem in Euclidean geometry, and I forget the name of it, but it basically says if this is 60 degrees, well, then this angle must be 60 degrees. Okay? Now, here's the thing. If this is the x-axis here like that, okay, how do you measure an angle? Well, you're supposed to measure an angle counterclockwise. So if you were to really do this right, you'd have to start measuring counterclockwise and go all the way around here like that. And then you'd say, oh, well, the angle is 360 minus 300 degrees. Perfectly fine. You can use that angle. Okay, here's another way to do it. So yeah, it's 60 degrees, but it's 60 degrees being measured clockwise. And when I first taught you to do this, I said to you, always measure counterclockwise. And it's positive angles measure counterclockwise. Well, I'm going to expand that a little bit because by this point you're probably pretty good at doing these things, solving these kinds of problems. So if you measure counterclockwise, that is red here, that's positive. Whoops, let me do it in red. If you measure counterclockwise, it's positive. But if you were, so counterclockwise is positive. Clockwise is negative. Okay, and so you can go right ahead and use 60 in there, but it's going to be negative 60, and that's because this is clockwise. Okay, so I hope that's not too confusing, but let me just go over it very quickly. We had this angle coming in. Let me go back to the other diagram, actually. It's probably easier to see it there. Okay, we had this vector coming in, and I tell you that this angle is 60 degrees. But that 60 degrees isn't the 60 degrees at the tail. That's the 60 degrees at the head. Okay, so you say, well, what do? Well, redraw the diagram, or at least that vector, and put the origin at the tail. And then say, okay, what's the angle that the tail makes with the x-axis? In most of these problems, though not all of them, it'll actually be a clockwise angle. So you start at the x-axis and then you would turn clockwise until you get down to the vector. And if you turn clockwise, then it's negative. Okay? So, so the angle that I'm going to use when I do my sine and cosine is actually going to be negative 60, not positive 60. All right? So if that's confusing, I mean, I could try to explain this in a different way, but there it is. Okay? So that's how that works. Okay? And now what? Well, we want the x component and the y component. And the x component is the magnitude 4, right there. Yeah, that's where that 4 came from. Multiplied by cosine and the angle. And the angle, well, that was that whole reasoning was to sort of explain why the angle is negative 60 and not positive 60. Okay? And if you put that in your calculator, 4 cosine negative 60, that turns out to be 2. Okay, cosine of 60, cosine of negative 60 is the same, and it turns out to be 2. But for the sine, it actually turns out to be negative. So if you do 4 sine negative 60, you get negative 3.464. Okay, and so that's how that 4 meters per second gets broken up into its x and y components. All right, now we're ready to start doing the calculations. I mean, because this is a 2D problem, you have to break up all your x and y pieces. You have to break up all your velocities into x and y pieces. Okay, so let me cut and paste that over here. Actually, I might as well just do it right to the end. Like that. Okay. And so let's start off with my analysis of the 7 kilogram mass. That's the one that we just looked at. The 7 kilogram mass, it has a V1x of 2 meters per second. And that's what I just did. Maybe I should just write here. How did I get that? That's going to be the 4 cosine of negative 60 degrees. Okay? And that's equal to 2. All right? And for the y component of that, that's the 4 sine negative 60 degrees, like that. And that turns out to be that negative 3.4641, like that. Okay? So that breaks up V1 into its x and y components. All right? And again, we have to do that because momentum, conservation of momentum, breaks up in x and y just the same. All right. Now for the other mass, which we'll call M2, well, it had no y component, and its x component was purely along the positive x direction. So in fact, here I could even say positive. Okay, over here maybe I'll just put a positive there. I've been putting positives in front of the positive and negatives in front of the velocities to be very clear about the directions. Okay, and so now what? Well, now we have conservation of momentum in the x direction, and there's that formula. It looks the same as above. So before it was m1v1 plus m2v2. Now it's, for the x component, m1v1x plus m2v2x. Okay? And for the y component, same thing, but not x, y. And there's that one, okay? So py, the y component of the momentum, is m1v1y plus m2v2y. Okay? And we have m's and we have the the velocity is broken up into the components right here. So you just substitute in there. Okay, so like what's m1? Well, m1 is 7. Okay, great, 7. V1x, what's that? V1x is 2. Okay, so we'll put a 2 in there. Okay, and so on. And then what's m2? It's 5. What's v2x? Well, v2x is 5. So 5 times 5 is 39. Okay, there we go. And same thing for py. Substituting in for there, we get this, and we get those values there. Okay, now those aren't velocities, those are momenta. So the total momentum x component before is 39 units kilogram meters per second. Y component before, negative 24.2487. Okay, and now what happens? Well, in this problem, the two masses come together and stick. Okay, and so afterwards we have only one mass. Okay, and what is that mass? Well, mass is conserved. So if you have a 7 kilogram and you have a 5 kilogram, together you get a combined mass of 12 kilograms. Let's just write that. So the combined mass after the collision is 12 kilograms. All right, great. Now what? Well, the momentum after is mvx. Okay, the x component is going to be mvx, where m, because there's only one mvx. Okay, so m is the combined mass, and vx is what you're trying to solve. It's the x component of the velocity of the combined mass afterwards. Okay, so before we had two masses, and so we had two mv's in there, but now we only have one, and so there's only one mv there. Okay, and so that means that this is just, I do that, it just means implied. Okay, so when I substitute in for px primed, well, that's the same as px, 39. And so I get that 39 is going to equal, and m, the total m is 12, and vx primed is what we're solving for. And so we got 39 is equal to 12 vx primed, and that tells us that vx primed is going to equal 3.25 meters per second. Okay, that gives us the x component of that velocity. Same thing for y. All right, so for y here, we've got py primed is mvy primed. Okay, and for py primed, it's the same as the before. So there's that. And whoops, I lost an equal sign in there. There we go. Okay, so the total momentum is going to equal 12 times. It's not that I lost it, I put it in the wrong place. There we go. Okay, so it's going to be 12 times vy primed, and that tells us that vy primed is going to be negative 2.02073, like that. Okay, so there we go. That answers the question. So the combined mass has x, y components of velocity equal to this, and no need to squish it up there, and that, and I'll round off here, meters per second. Okay, so there we go. Actually, put it on the, I'm obsessing here about form. There we go. So that answers the first question. Okay, now what? Well, same thing. Well, not same thing. Same values, but now converted into polar. And so you say, well, how do I convert from Cartesian to polar? Well, to get the magnitude is obtained by the square root of the x component squared plus the y component squared. Okay, so if you've done this a lot of times, I didn't even bother with the formula because you should know it by now. But here's the x component right there. So 3.25 squared. There's the y component. And squared, whoops, I forgot the squared piece here. I hope I did this right on the calculator. Give me a sec to check that number, because I might have missed that. Uh, 3.83, and sure enough, I I did it wrong. There we go. 3.83 meters per second. Okay, so there's the magnitude of the velocity. That's actually how fast it's going. Okay, so remember, the components are not how fast it's going, it's how fast the projections along the x and y axis are going. That's actually how fast it's going. And then the other thing I can ask for is the angle, theta. And the angle theta is going to equal the inverse tangent of the y component divided by the x component. At this point, you're going to say, wait a sec, this is in quadrant 4. Shouldn't I be adding 360? You can. You absolutely can add 360, okay? But I'm going to show you something a little bit different now, okay? Yeah, 360 is correct because you're in quadrant 4, and that would give you a positive number. But you can always just keep the negative angle, okay? And it's perfectly fine, provided you use that understanding that I gave you a minute ago, that the negative angle means measured clockwise, okay? And so the angle is negative 31.9. And is that right? Does that make sense? Yeah. Let's go back to the first diagram. Not this one, but this one. Okay. And remember we said, oh, feels like it should be going that way. Okay, just intuitive. Yeah. So again, we normally measure our angles this way. Okay, like that, because counterclockwise is positive. But if we measure, if it's a negative angle, we can measure it that way. And this one's negative 31.9 degrees, like that. Okay. And does that fit what we expected? Yeah, it does. Okay. Now, if we had actually added the 360, you know what would have happened? We would have gotten this angle here, all the way around and to there. Okay. Which is totally correct because it still points in the same direction. It's just one is measuring it going all the way around counterclockwise, and the other one is measuring it going clockwise. The clockwise has the negative, the counterclockwise has the positive. Okay. And so just clean up here, switch back. And so over here, if you leave the angle as negative, that means start at the x-axis and measure clockwise. If you add the 360, that means, you know, you're going to get a positive. It means start at the x-axis and measure counterclockwise. And you'll wind up in the same place, but one, you'll go all the way around counterclockwise. The other one, you'll go more directly clockwise, okay? And so, you know, both are totally legitimate, okay? So whether you add the 360 or not depends on whether you want the positive or the negative angle, all right? And that's it. I just thought I'd explain this because I've added this new understanding of, you know, the angle of a vector. Now, quadrants 2 and 3, you might go, well, do I still have to add 180 in quadrants 2 and 3? Yes, yes, you do, okay? So there's no getting around that, okay? But here, when you're in quadrant 4, adding that 360 is optional with this extra interpretation, okay? So there we go. That's the end of the class. Now I still have to do center of mass, but like I said, I'll do that next week. There's a lot to conservation of momentum. I mean, when you go through the lecture, I think it turned out to be just like about an hour and 40 minutes, all the material. And it seems, you know, oh, this is pretty obvious, but you know, the questions can get pretty subtle. So you know, we're going to spend a little bit of time on that. All right. So let me see if there's any questions in the chat. If not, we're done, guys. If that's okay, let me just ask here. If everyone is okay, we're done with the class. Okay. Again, you don't have everything that you need to solve the assignment, but the center of mass problems are pretty easy. And I will do them. I will do some examples next week. And that's why I didn't make it due this Friday or tomorrow. I thought it would be a little bit too squished. There's too much material. So, okay. So I'm not seeing any questions, and I'm seeing people leaving already. So let me say goodbye, and you know, catch me on a Google Hangout if you have any questions. Okay. Bye-bye. Bye, Pearl.